Welcome to this lecture on getting the most out of your machine learning models. We will explore key techniques to enhance model performance and robustness, covering advanced architectural considerations, systematic hyperparameter tuning, and the power of model ensembling. Our journey begins with advanced architecture patterns. Here, architecture extends beyond deep learning to include the design of feature engineering pipelines, model component choices, and how models are chained together. We delve into feature engineering pipelines as a crucial aspect, demonstrating how steps like transformation and scaling become integral to a model's architecture. Mathematically, this involves concepts like polynomial transformation for features or standardization, which adjusts data to a common scale using mean and standard deviation. Next, we see a practical pipeline example. Using scikit-learn and the breast cancer dataset, we construct a pipeline that first standardizes the data using standard scalar and then applies a logistic regression classifier. After splitting the data into training and testing sets, the pipeline is trained, predictions are made, and the model's accuracy is evaluated, showing a result of approximately 98.25% accuracy. Moving on to hyperparameter optimization, we understand that hyperparameters are external configuration settings not learned from data, such as regularization strength or the number of trees in a forest. Optimizing these is vital for performance, generalization, and efficiency, preventing underfitting or overfitting. We discuss common techniques, grid search, which systematically checks all combinations within a predefined set, guaranteeing the best combination but being computationally expensive, and random search, which samples randomly from distributions, often finding good solutions faster in high-dimensional spaces without guaranteeing the absolute best. We also note the mathematical concept of a search space, where the total combinations for grid search multiply the number of values for each hyperparameter. An example of hyperparameter optimization with grid search is then presented. We apply grid search CV to our pipeline, specifically tuning the logistic regression component's inverse of regularization strength C and its solver algorithm. The process involves fitting grid search with five-fold cross-validation, and the output reveals the best hyperparameters found, for example, C equal to 0.1 and solver as liblinear, along with the best cross-validation accuracy of 97.74%. Finally, the best tuned model's test accuracy is evaluated, achieving an impressive 99.42%. The notebook then transitions to model ensembling, a technique where multiple models are combined to achieve superior results. The core idea is that combining diverse models can compensate for individual errors, leading to more robust and accurate predictions. The benefits include reduced variance, improved accuracy, and increased robustness against overfitting. We explore three main types of ensemble methods: bagging, which trains multiple models on different data subsets and averages or majority votes their predictions, with random forest as a prime example. For regression, this involves averaging the predictions of individual models. Boosting sequentially builds models, with each new model correcting the errors of previous ones, exemplified by gradient boosting and XGBoost. Lastly, stacking combines predictions of multiple base models using another learning algorithm known as a meta-learner, where base model predictions serve as input features for this meta-learner. An ensemble example with voting classifier illustrates this concept. We define three individual estimators, a pipeline with standard scalar and logistic regression, a random forest classifier, and a gradient boosting classifier. These are combined into a voting classifier using hard voting. The ensemble is trained and its accuracy is evaluated, showing an accuracy of 97.08%. For comparison, the individual model accuracies are also displayed, revealing that the logistic regression pipeline achieved 98.25%, random forest 97.08%, and gradient boosting 95.91%. Following this, we look at an ensemble example with stacking classifier. Stacking uses a meta-learner to combine base model predictions We use the same base estimators as before: logistic regression, random forest, and gradient boosting, and a logistic regression as our final estimator or meta-learner. The stacking classifier is trained with 5-fold cross-validation to generate out-of-fold predictions. After training, predictions are made on the test set, and the stacking ensemble's accuracy is evaluated, reaching 98.25%. In conclusion, by diligently applying advanced architectural patterns through pipelines and effective feature engineering, systematically optimizing hyperparameters, and harnessing the collective power of ensemble methods, we can significantly enhance the performance, robustness, and generalization capabilities of machine learning models.